Alright, hello everyone. My name is Gurkarn Gill, and I want to start off this video by saying something that my physics teacher encouraged us to think or write down before starting any kind of work, whether it be an assignment or an exam or a video project like this. And it goes, I love physics and I'm good at solving problems. And now, obviously, you can replace physics with whatever you're actually working on. And this is more for positive thinking and positive reinforcement as it has its benefits, believe it or not. So the topic that I wanted to talk about is something that originated in physics, specifically in quantum mechanics, but it's definitely seeped into our pop culture. I've definitely heard it mentioned in at least one show, in science YouTube videos, and there's even a theory that the name of Walter White's alter ego was inspired by this topic, which I haven't confirmed due to laziness. But anyways, so the topic that I want to talk about is Heisenberg's uncertainty principle. Now, I'm aware it's a complex topic that has a lot of implications, so I will try to summarize it and try to simplify it for the purposes of this video. So before I get into the details, I want to get into how this principle actually came about a little bit into the background. So it started with a German theoretical physicist named Werner Heisenberg, and he is considered one of the key pioneers of quantum mechanics. And he published the paper for this specific principle in 1927 and actually won a Nobel Prize. And so yeah, this principle is a very big deal. So basically, Heisenberg had a thought experiment where he considered trying to measure the location of an electron using a microscope, specifically a gamma ray microscope. So he reasoned that the high energy light from the microscope that's being used to measure the electron would actually give it a kick and actually change its momentum. Now, if you try to use a higher resolution microscope, it would need a higher energy light. Well, all that would do is give the electron an even bigger kick and in turn a larger momentum. So what this meant is that you can never actually measure the location of an object with an infinite precision without the momentum being affected. Or a more proper definition would be Heisenberg's uncertainty principle tells us that it is impossible to simultaneously measure the position and momentum of a particle with infinite precision. Excuse me. So this may seem confusing because one might think that there's a limitation on the device, the measuring device itself, but it's actually more like a limitation on what properties an object can have. So just a bit more of an explanation. Uncertainty exists because everything in the universe behaves more like a particle and a wave at the same time. Particles exist in a single space at any instant of time, whereas waves are more like disturbances spread out in space, like ripples in water. And you can clearly identify wave features as a whole, such as wavelength or amplitude, but you can't really assign a position to a wave. But you can assign a momentum, which is related to its wavelength. So you can measure a particle's position, and you can measure you can measure the speed of a wave. And now combining these two, you get a wave packet where you can measure both the location and speed of an object, but you have to lose some amount of uncertainty of both. Although you can have good probabilities of either of these qualities. This involves taking waves and adding them together until you have a wave pulse, so that it has a position more or less that can be measured, but that's a bit of a rabbit hole, so I'll leave that out for now. Ta-da! Here's the equation, and I'll just quickly describe the variables so it doesn't look like a bunch of symbols and stuff. So usually x is considered a position and p is considered the momentum, and in this case delta x is the uncertainty in position and delta p is uncertainty in momentum. And on the right side of the equation you have h over 4 pi. H is actually Planck's constant, but for the purposes of this video, this right side of this equation is just a really small number that the left side is compared to. So this is basically a limit, kind of like the limit on how fast something can go, kind of like the speed of light. So a very simple way to explain this principle and equation is through an experiment that was actually done on Veritasium's YouTube channel. That's actually the channel that initially got me very interested in this topic. I'll link to the video down below. So what he did was he set up an experiment where he shot a laser at a wall. Simple enough, right? But in between the laser and the wall, he placed a slit that the laser passed through. Now this slit is actually adjustable, as represented by the dotted lines, the dotted blue lines. So you can turn a knob and the slit will shrink and will let less light through it and hit the wall, as represented by the dotted lines. So he started it and all the light passed through, and he slowly made the slit smaller and smaller. So he started with all the light passing through, and he slowly made the slit smaller and smaller. And what we notice when we look at the light on the wall as he's doing this is that, as you can see, that the light is actually, it's decreasing in width. But at some point, at some limit, the light actually starts to become wider. Oh look, I made a scary face. Now normally that wouldn't make any sense. You are letting less light through, but the light on the wall is clearly getting wider. What the heck, right? So the way to explain this using the equation is that the key is that the uncertainty of momentum multiplied the uncertainty in position has to be greater than or equal to this really small number. This is because when you narrow the slit, you are actually decreasing delta x. So you are getting more precise about where the photons are passing through the slit. But if you decrease delta x, then delta p has to increase. Just a side note, this delta p is in the x direction. So at some point you hit this limit and delta p has to increase. And this is insane to think about. And in the words of Veritasium, it's crazy because it's so non-intuitive, but it's the way that the world works. So that's all I have for today. That was the Heisenberg's uncertainty principle as told by me. Hopefully you guys got you guys learned something and got a better understanding of this principle. And please check out the link below to Veritasium's video, as his experiment helped me get a better understanding of this principle. Oh, and Charles, you said no one ever shows their face in these videos, so here's mine while I was working on the video. See ya.